To recapitulate again, but for motion at a constant acceleration, remember we are talking about constant acceleration here. A is constant, average A is the same as A. If we have motion only along one direction, so that would be A sub x. Average A sub x is A sub x. Now if we go to the position final is position initial plus VIT plus 1/2 of AT squared. Remember, this is for constant acceleration. We developed this equation for displacement. Remember, displacement is PF minus PI. So if I write displacement is equal to VIT plus 1/2 of AT squared, like we had before, and then we can move the PI to the other side, so that's plus on the other side. That's where that equation is from. Okay. Now final velocity is initial velocity plus acceleration times time. This is correct all the time. Displacement is average velocity times time. Okay, and now we have one last equation. Okay, let's use the eraser here. Where do we get that last equation from? This is, what if we don't have time? How do we find displacement? Okay, let's go back to this equation here. Now that equation, I'm going to write it in terms of displacement, is equal to average velocity, the I should not have been there, average velocity times time. Now let's write it again. Average velocity, if I have constant acceleration, that would be VI plus VF over 2, and then time, I'm going to find it from this equation. So time is equal to VF minus VI over A. So I'm going to replace it here. VF minus VI over A. So displacement is equal to the product of these two. So that's going to be 2A in the denominator, and then VF plus VI times VF minus VI. Multiply both sides by 2A, we get 2AD, that's equal, and then I'm going to factor out that one, so VF times VF is VF squared, and then minus VF VI, and then plus VF VI, and then minus VI squared. Is it? So that's the equation here, and you notice we have minus VF VI plus VF VI, so these two, they cancel each other out. So we have VF squared minus VI squared. So that's what we have here. Strictly speaking, I didn't write it as squared, just to show us, because vectors usually speak of what we call scalar products. So I kept it this way. So VF times VF minus VI times VI is equal to AD. But if we are along one direction, that translates as Vx f squared minus Vxi squared is equal to AX times the displacement along the x. So So I use the eraser here. These are expressions in general. Along the x, these are expressions. So constant acceleration ax, then my displacement along the x, we write it as x. xf is equal to xi plus vxit plus 1/2 of axt squared. Quite often people might not write the x here and the x here and just write xf minus xi is equal vit plus 1/2 of at squared. Sometimes instead of the I, they write 0, v0t. Okay, vxf is equal to vxi plus axt, and then the displacement, which is the change in position, xf minus xi is vx times t, and then vf squared minus vi squared is equal to a times displacement, which is xf minus xi. These are our kinematic equations for motion at constant acceleration.